velocity as a function of time, this is just going to be the derivative with respect to time of the position function. Like this. So the derivative of this position function is going to be 18 times t minus 2 squared. Like that. And then if you want to find your acceleration as a function of time, acceleration is just the derivative with respect to time of your velocity function. So that should just be 36 times t minus 2. It's okay. So we've just worked one example. It's an old example from like Calculus 1, where you maybe remember if you're given a position function, you can find the velocity and acceleration just by taking the derivative with respect to time. Yeah, cool. So then we're all caught up, and we remember Calculus 1. Now we're going to say that we have an object that moves through three-dimensional space, and so we have the x-coordinate and the y-coordinate and the z-coordinate as a function of time. Right? So I have x of t, y of t, z of t. And it's going to be really, really similar, same kind of problem. We can find the velocity of the object as a function of time just by looking at my position and taking the derivative with respect to time. So,
what's the difference between speed and velocity?
whenever I say speed, what I mean is like the magnitude of the velocity. So velocity is like, magnitude and direction. Velocity tells you the direction you're moving. Speed doesn't really tell you the direction you're moving. It just tells you how fast you're going, yeah. So, then the derivative of natural log is going to be 1 over t. The derivative of t to the negative 2 power would be negative 2t to the negative 3 power. And then t to the 4th power would be 4t to the 3rd power. So there's your velocity vector. Your acceleration vector is, again, you just take the derivative with respect to t of a velocity vector. And so that should be negative t to the negative 2 power, 6t to the negative 4 power, and 12t squared. And then like Abdullah pointed out, the speed is just the norm of the velocity vector, right? So the speed is going to be the square root of 1 over t squared plus 4t to the negative 6 power plus 16t to the 6th power. Does that make sense? Pretty straightforward. Kind of like exactly what you did in Calculus 1, but now we're just doing it 3 times for the 3 components instead of the 1 component. Okay. New example. So we have a spaceship. And so we have to define some coordinate system in space, so maybe the coordinate system is relative to Earth and the North Pole and whatever else. But we know that the sum of the forces on the ship, if you've ever drawn a free body diagram in physics, you sort of draw all the forces acting on the ship, gravity and the propulsion from the thrusters and whatever, and then take the sum of the forces And that vector sort of describes the direction of the acceleration of the object. And so this is the resulting acceleration vector as a function of time. Beyond this, we also know what the position of the ship is and what the velocity of the ship is at time t equals 0, right? So if I say p of 0 and v of 0, I'm talking about when t is equal to 0. And the question that we're now asking is, where will the ship be at time t equals 10? So we know a of t is cosine t, sine t, 8. So v of t is going to be the antiderivative of a of t with respect to t, right? So that means v of t, my velocity vector, is going to be something like, what's antiderivative of cosine? Sine. What's antiderivative of sine? Negative cosine. And antiderivative of 8 is 8t. Again, because this is antiderivatives, we can add some constant. So plus c1, plus c2, plus c3. And those are just some constants. I can figure out... choked on a frozen carrot. I can figure out what those constants are by reminding myself that v of 0, my velocity at time t equals 0, had to be 1, 1, negative 1. So these are 1, 1, negative 1. What is the value of c1? Yeah, it has to be 1 because sine of 0 is 0. Okay. Cosine of 0 is 1. So this is negative 1 plus some constant equals positive 1. So c2 is 2. Okay. And then lastly, what is c3? Negative 1. So that means my velocity vector is going to be sine of t plus 1 negative cosine t plus 2 and 8t plus, minus 1. That makes sense so far? Okay. Now, my position vector is going to be the antiderivative of my velocity vector. So my position vector, what's the antiderivative of sine? Negative cosine. The antiderivative of 1 is t. Okay. What's the antiderivative of negative cosine? Negative sine. Antiderivative of 2 will be 2t. And then the antiderivative of 8t is 4t squared minus t. And then, because we just took the antiderivative, we can add constants. So I'll say plus c4 plus c5 plus c6. Now we can figure out what are c4, c5, and c6 if we remember that p of 0 is 0, 0, 0. So what should c4 be? 1? Yeah. What should c5 be? Mm-hmm. And what should c6 be? Yeah. So altogether, my position at time t as like a little coordinate triple, x, y, z coordinates, should be given by negative cosine t plus t plus 1, comma, negative sine t plus 2t, comma, 4t squared minus t. And so my question was asking, what is my position when t is equal to 10? So we just have to plug in 10 and find that p of 10 is, well, you'd need to use your calculator, right? Because I don't know what cosine of 10 is. But it would be negative cosine 10 plus 10 plus 1. Negative sine of 10 plus 20. And then 400 minus 10. So 390 for my z coordinate. Okay. So, I don't have a calculator. I'm not going to worry about plugging it in because you guys know how to plug it in. Really, the interesting part about this problem is just remembering that velocity is going to be the antiderivative of acceleration, and position is the antiderivative of velocity. Each time you take an antiderivative, you can always throw in those constants. You can add a constant to each component of your vectors. And then you can sort of figure out what those constants should be if you're given these. And I mentioned this yesterday, I think. Stephen had a good question, and so we talked about this. These are called initial conditions because it tells you about the velocity and the position at time t equals 0. So these are like the initial velocity and the initial position of the spacecraft. So these are helping you figure out what those constants are. So far, so good? Ugh. Yeah. For those of you that are coming in late, I put my vegetables in the break room refrigerator, and someone turned the break room refrigerator up to like maximum or whatever, coldest, and so it froze everything in the refrigerator. So now my veggies are frozen, and now that they're thawing out, they're really nasty. Like, don't ever freeze vegetables and then thaw them because they're like really gross now. Okay. Kind of mad about that. It's like $3 worth of veggies right there. Okay. New example. It says a cannon fires a cannonball. So here's my little cannon. And it's firing a cannonball. Very realistic. From ground level, that's supposed to be flat, but at an angle of 30 degrees. Okay, so the path of this cannonball, is going to be a parabola. You've probably heard that before, different math classes. And again, this angle that it's initially shot at is going to be a 30-degree angle with the ground. And the ball hits the ground 50 meters away from the cannon. After the cannonball is shot out of the cannon, we're going to ignore air resistance. And so ignoring air resistance, really the only force acting on the cannonball after it leaves the cannon is going to be gravity. There's a bunch of questions we want to ask. Maybe you've already done this in like physics 1. But we want to ask, what was the initial speed of the ball as it's leaving the cannon barrel? Right, so if we need it to travel 50 meters, how fast does it need to be going? What is the maximum height of the ball? So that would happen right here. This point where it reaches the top of the parabola is called the apogee. A-P-O-G-E-E. So we're talking about what's the height or the altitude at the apogee. And then the other thing is how long, and then it's like what's the duration, like time-wise. How long is the ball traveling through the air? So we sometimes call this hang time. Okay, so for one thing, we don't actually need to worry about 3D coordinates here. All right, so this ball is going to be traveling in a plane. And so I'm going to go ahead and label this direction, the vertical direction, y. And then this horizontal direction, I'll label that x. So I really only have to talk about two-dimensional vectors and coordinate pairs whenever I talk about position. So the position of the cannonball at time t equals 0, I'm going to label that point 0, 0. Okay? The velocity of the cannonball at time t equals 0 is going to be whatever the velocity is, right? Like as it's exiting the barrel of the cannon. And so I'm going to come up with a little variable for my speed. I don't know what I should name it. I would use s, but s's look a lot like 5s. And I don't want to get confused. So maybe I'll name it like name it q, just to be exciting. So q is going to be the speed. And so my velocity is going to be whatever that speed is times cosine of 30 degrees in the x direction. And then in the y direction, the initial velocity is going to be that initial speed times sine of 30 degrees. Does everybody understand how I got the initial velocity? I don't actually know what the initial speed was. That's actually one of the questions. That's the first question we're trying to answer is, what was this initial speed? We want to know what is that q of the ball as it leaves the cannon barrel. But we're going to find that here in a minute. Hopefully. And then, the acceleration that's acting on the ball. I don't just care about initial acceleration, but actually everywhere the acceleration is constant, because the acceleration due to gravity is constant. And that's acting in the negative y direction with an acceleration of 9.8 meters per second. And so it doesn't matter what the time t is, you're always going to have an acceleration acting with negative 9.8 in the y direction and 0 in the x direction, just because that's how gravity works. So what is cosine of 30 degrees? Root 3 over 2? And what is sine of 30 degrees? 1/2, yeah. Okay. So that's my initial velocity. Now we remember that velocity, the function, is the antiderivative of acceleration, the function. Okay? So my velocity function is going to be, what's the antiderivative of 0?
It's constant.
Yeah, just any constant, right? You take the derivative of any constant, it gives you 0. So that's my antiderivative. And then what's the antiderivative of negative 9.8?
Negative 9.8.
Yeah. Plus another constant. Now, to figure out what these constants are, I need to look at my initial velocity. So I know that when t is equal to 0, this is my velocity, right? And so if I set t equal to 0, I can figure out what those constants are. And including the constants, my formula for velocity is going to be root 3 over 2q, comma, negative 9.8 t plus 1/2 q. So the constants c1 and c2 are just my initial velocity components. All right. Now, what about position? So my position function is going to be the antiderivative of my velocity function with respect to time. And so that is going to be the antiderivative of this So the antiderivative of root 3 over 2q is going to be root 3 over 2 qt plus a constant. And then the antiderivative of negative 9.8t is negative 4.9t squared. The antiderivative of 1/2 q is going to be plus 1/2 qt, and then I get to add a constant. So that is my position function. And then, of course, I'm remembering that position at time t equals 0, my initial position. That was 0, 0. And so whenever I set t equal to 0, I want everything to be 0. That means that I don't actually need these constants, right? C3 should be 0 and C4 should be 0. So that's how I get my position as a function of t. Write it out again. So that's root 3 over 2 qt and then negative 4.9 t squared plus 1/2 qt. All right, let's revisit our questions now that we've sort of figured out our velocity and our position functions. So one thing we have not figured out yet is we haven't figured out what this lowercase q is. We haven't figured out what is the initial speed of the ball as it left the cannon barrel. We also haven't figured out what is the maximum height of the ball, and we haven't figured out how long the ball was traveling through the air. I think I can make a little bit of progress on the second question. What was the maximum height? Because the max height should occur when the y component of the velocity is 0. Yeah. So if you think about it, this ball is traveling up and then it travels down. So initially the y component of the velocity is positive, and then as it's traveling back down towards Earth, the y component of the velocity should be negative. And since this is a continuous function, we're going from positive to negative. There's a point where the vertical component of the velocity is 0. That point is going to be my apogee. And so I get the maximum height when I set the y component of my velocity to 0. The y component of my velocity is negative 9.8t plus 1/2 q. Negative 9.8t plus 1/2 q. So negative 9.8t plus 1/2 q equals 0. Okay. So I'm going to call this value of t, this particular time value, I'm going to call it t with a little subscript a, because I'm going to call ta the time at my apogee, the time when I reach my highest point. So now, if I only knew q, my initial speed, then I could figure out the time of my apogee, right? I've got this little function right here, so I could write t of a is equal to negative 1/2 q divided by negative 9.8, so it would be 1 over 2 times 9.8 q. I think. Probably. So anyways, I've got this formula that tells me the time at my apogee if I only knew my initial speed, and eventually I'll find out my initial speed, and then I can find the time at the apogee. And if I knew the time at the apogee, I just have to plug that into my y component of my position to find out the height at the apogee. So making a little bit of progress there on my second question. Let's talk about the time the ball was traveling through the air. So I'm going to call this time TF, like it's the final time. Basically the moment when the ball hits the ground again, that's what I'm going to call my final time, so T subscript F. I can find this just by knowing that my ball traveled 50 meters in the x direction, and I know that the speed in the x direction was constant, right? My velocity x component was root 3 over 2q. And so if I say this, T final is root 3 over 2q. Whoops, sorry. It should be 50 meters divided by root 3 over 2q meters per second gives me seconds, so that's the unit of time. So in other words, I could say that this is 100 divided by root 3q. So again, if I only knew my initial speed, that lowercase q, then I could also figure out the time that the ball hits the ground, right? My final time. Figure out my hang time. Let's see what else I know. If I want to find that final time, let me try another method, try another approach here. The position, whenever I'm talking about my final time, TF, that should be a position where the x component is 50 and the y component is 0, okay? And that means if I set this component of my function equal to 0, that's another way I could discover the final time. So setting negative 4.9 t squared plus 1/2 qt equals 0, let's see what I get. Can factor out a t, and I get 1/2 q minus 4.9 t equals 0. So there's two solutions, because this is a quadratic equation. One solution would just be setting t equal to 0, and of course that's just telling you that whenever the time is equal to 0, then the y coordinate of the cannonball is at the ground level. It's inside the cannon, about to be fired. The other solution is going to be the solution that I get if I just set 1/2 q minus 4.9 t equals 0, or in other words, 1/2 q is equal to 4.9 t. And this t, once I solve this equation, is going to be my final time. And so that's going to be 1 over 9.8 q is equal to tf. Is that exactly what I had before? Not exactly. Okay, so before I set my final time, TF, to 100 over root 3Q. And now I have something a little bit different. Right? So I know that the final time has to be equal to that based on what we did earlier, and that at the same time. So now I actually have a little equation. Let me rewrite it. I can write Q over 9.8 must be equal to 100 over root 3q. So, gotta do a little rearranging. multiply both sides by q, and I get q squared on the left. And then multiply both sides by 9.8, and I get this on the right. So as long as everything's correct in our work so far, that is going to be my initial speed. Somebody with a calculator, tell me what is the square root of 980 divided by square root 3? You say 23? 23.79 meters per second. Okay. Sounds kind of reasonable.
If it's a cannon.
Hmm?
If it's a cannon.
Yeah, we should be able to shoot a cannonball pretty far. Although I'm just thinking 50 meters is not all that far.
Depending on the weight of the cannonball.
But yeah, I don't know. I'm trying to think. So let's see what we get for our hang time if I plug in that. So it would be 100 over square root 3 times q. So in your calculator, somebody help me with this. Right? Is that the right formula? Just making sure. Yeah, okay. Huh?
2.43.
Okay, 2.43. That sounds about right. Like if you're shooting a cannon and the ball only travels 50 meters, it only spends 2.5 seconds in the air. I guess. Good enough. I mean, it's not a crazy number. It's not like 200 seconds, so I'm feeling better about this.
Plus, it's not really traveling 50. It's more like a curve. So it's a little more.
Let's see. What else? So the time at the apogee should be 1 over 2 times 9.8 q. Wait. It was 1 over 2 times 9.8 times q, right? No, times q at the end, not in the denominator. So what is that time?
Yes. That's greater than the final time.
It shouldn't be.
1.21.
1.2 what?
2.1.
Yeah. It should be about half, right? The apogee should, I mean, we know that parabolas are symmetric, and since we're starting from ground level and ending at ground level, we would expect the apogee to be like the half point, the half of the hang time.
Oh.
And that's what we have, pretty much, with rounding.
29.8 or 2.8?
That's 2 times 9.8.
Oh,
So that's like
yeah,
that's like sorry,
yeah,
1
that was
over
1 over
19.6 q. Yeah. Okay. So very good. In fact, you could use that fact that the apogee time is like half of the total hang time if you knew you were starting from ground level and ending at ground level. But these questions can be different. Like, what if your cannon was sitting on a cliff and then it shoots the ball and then it lands into the canyon? That's like at a different altitude. Then the apogee time won't be half of the hang time. Or if your cannon is in the if your cannon is in the canyon. If it's like at a lower altitude and it's shooting up a cliff, or there's different ways you could phrase this type of question where you can't use that fact. And so I was trying to avoid just saying that the apogee time was half of the final time, because that's not always true. But in this case, it was true just because we were starting at ground level and ending at ground level. Okay, so we have the hang time. That was one of my questions. We have the apogee time. And now that we have the apogee time, we can find the maximum height too. So the maximum height occurs at the apogee, and what I need to find the height is just the y component of my position function. So I'll try to highlight that here. The y component of my position function is this. And so to find the apogee, the height there, that's going to be negative 4.9 times, what did I say, 1.21 squared plus 1/2 q, where q was 23.79. Times 1.21. There we go. So finally, using the y component of my position function, plugging in 1.21 for the time, 23.79 for the initial speed. Somebody help me with your calculator and tell me what is that height at the apogee. Did you say 7.22?